in the year 2013. He completed his master's from Department of Electronics and Communication Engineering, NIT Rourkela. He was a recipient of Canadian Research Fellowship from Department of Foreign Affairs and Intern Grade, Government of Canada for the year 2009 and 10, with which he has worked at the University of Western Ontario, Canada. He was awarded Best Thesis Award at a conference SOC Pros 2015 by IIT Roorkee. So his main focus is in the field of machine learning, deep learning, remote sensing, meta-heuristic algorithms, and adaptive signal processing. So Sir has received several travel grants from ACRB, UGC, INSA, INAE, and all. He's also in charge of digital signal image processing lab at MNIT Jaipur. He has supervised several PhD scholars and master theses. He has published several papers in international journals and conferences of high repute. So with this, now I request Professor Nanda to kindly start the session.
Thank you, Dr. Deepak, for giving me an opportunity to interact with the participants.
Pleasure, sir. Pleasure.
In this particular domain. So for the next 1 hour, I will be discussing about the application of these algorithms, especially the meta-heuristics for hyperspectral image analysis. Let me share my presentation. Dr. Deepak, can you check my slides are visible?
Visible, sir. Visible, you are audible also, sir.
And when I am writing on this, is it working? Just
yeah, you can see your cursor.
Please have a look.
Yeah. Red color. Yeah, red color marker.
Yes, red color marker. Yes. Okay.
Yes, sir. Over to you,
sir. Thank you. So hyperspectral imaging is a very important type of images for analysis. We can able to observe here. I have given an example of a hyperspectral imaging. Okay, this particular image is a stack of two-dimensional images. Okay, as you can able to observe here that in this particular image, there is a river which has been merged to a sea, and on both sides of the rivers, there are hilly mountains and greenery areas are there. So this particular portion, if you will observe, this particular portion is the river merged with the sea, and this is terrain region, reverse path, and there is greenery region this particular zone, and also terrain region this particular path. And this particular image has been captured from satellite. Okay, and how this particular image has been captured? By sending a signal of specific bandwidth from the satellite to the Earth's surface. And when these particular signals get reflected from the Earth's surface back to the satellite, and the various wavelengths get collected at the satellite, and they are being perceived as an image that is an hyperspectral image. So over here, the images are created with the spectrums, and there are many types of spectrums. You can say long wavelengths, when we perceive it, perceived it as red color. Medium wavelengths, they are perceived as green color, and short wavelengths, they are perceived as blue color. So with these three things, there are RGB combinations we can able to get. And you can observe that this one particular image is one particular wavelength. And for multiple wavelength, there is a stack of images over here. Okay. So in normal image, we will have image pixel values in X and Y. And along with that, there is a lambda component is there in the Z direction. So that make the hyperspectral imaging special. So over here, each image is representation with respect to the wavelength, and the images are combined in the form of a three-dimensional matrix. That is, xy represents the two dimension, and lambda represents the spectral dimension of the wavelength. So these images are captured by various spectrometers, and NASA's Airborne Visible Infrared Imaging Spectrometer, known as AVIRIS, is very popular in capturing this particular type of image. So the hyperspectral image and multispectral image, there is a very small difference between that. Hyperspectral images are actually captured in continuous band of wavelengths. Okay, so you can take one example like 400 to 1100 nanometer with step size of 1 nanometer. These particular continuous bands, these images are created. And another thing, when we take it in non-continuous bands, then those images are known as multi-band imaging or multispectral images. Okay, so that same wavelength, that is 400 to 11 nanometer, whatever we have taken for both the image sets, but here with a step size of 20 nanometer, the images get collected. So they are non-continuous bands, we can able to say over here. So on this particular aspect, we will be focusing on two important problems over here. One is the segmentation of these particular images for meaningful partition and the importance of each particular partition in solving any particular problem. Then the second problem we are going to discuss is effective band selection for reducing the size and retaining the important information so that the hyperspectral image can be processed. If it is a 10 GB, 15 GB image, it is not possible to do effective processing of such a large image. So we have to select few bands out of hundreds of bands so that the meaningful portions of the image can be processed and inferred out of it. So that is very important. So considering the important application of hyperspectral images, the first problem is image segmentation. You can able to observe that hyperspectral image segmentation has very much potential applications. One of the important application is shown over here is fire detection. In a forest or in any particular mountain area, if we effectively wish to determine where the portion of the fire has captured in which particular portion of the forest, then from the satellite captured image, we can able to determine, we can able to segment the fire portion. Okay, and we can also predict that the fire will move in which particular direction or so. Then another important application is glacier detection. In glacier detection, it is very important because the igloo houses are just lying below the glacier, and if we cannot able to detect and predict the uh, glacier portions, then it will be very difficult for the survival for the Eskimos, because at any time if the glacier melts, then their houses along with them, all of them will get down inside the ice cubes. So that will be very dangerous for their survival. So that's why the glacier detection is another important problem. Then water detection on the top of the mountains, many times the water bodies will be there. And if we can effectively able to detect the water bodies which are there at remote locations also, then it will be helpful if we pass on the message to the nearby locality people, they will get immensely benefited. Another important application of this hyperspectral imaging is landscape monitoring. So you can able to observe that in many portions of the earth, there are small islands are there near to the seashores. Okay, when there is tsunami or high tides are there, there is highly likely that these islands may get merged, or the water near the particular seashore that will uh, grab the particular portion of the land. So in order to avoid such type of hazard scenarios, we may give warning by considering the particular analysis. And timely warning can save a lot of people's life. So these are very important potential application of the image segmentation, especially from the satellite imaging, hyperspectral images. There are many methods which have effectively been applied for these hyperspectral image segmentation, like the graph cut method, binary based image segmentation, multi-level image segmentation. There are region based segmentation, edge detection based segmentation method. Mars RCNN can be applied. CNN and its all variants, they can also be effectively applied for image segmentation. So over here, one particular satellite image, hyperspectral image, has been divided into 5 different clusters or group you can able to observe. If you will observe that the A is the original image without clouds, okay, it has been divided into 4 different categories, this B, C, D, and E. The C portions contains the water bodies. Only the river portion has been given over here. The D and E, they are representing the greenery and the terrain region. So like that, we can able to divide this particular image into various portion based upon the pixel intensity, and each of them will represent a significant portion of the image from which we can further analyze and determine significant inferences. So how to segregate this image into effective partition is a partitional clustering problem. Okay, here I am talking about unsupervised learning method, and one of the most important unsupervised learning method is partitional clustering. So over here, if you consider a two-dimensional image and you are going to partition it into n m number of groups, then this is the image you can consider P11 to P1D, one particular row, and this is n particular row and D dimension. Okay, so this particular data set we can able to group into m number of clusters in such a way that these particular conditions should be satisfied, that none of the clusters should be empty. Each cluster should have certain number of pixel values. Then between two different clusters, there should not be any common element should be there. Means one particular pixel cannot be belongs to water as well as terrain category, or water and vegetation. One particular pixel cannot belongs to two different category. So all the pixels that representing water, they will be grouped into one category. All those pixels which are representing vegetation, they will be in another cluster. So in between clusters, the number of elements should be 5. Okay. Then if the entire image have been bifurcated into 3 or 4 portion, suppose 3 portion it has been bifurcated, then the summation of all these 3 portions is equal to the particular image. So that is what is represented with this third particular condition. So most popular algorithm, very easy to do the segmentation, is k-means clustering algorithm. This was invented around 1960. Okay, and obviously the inventor are from Bell, and the researcher name is Lloyd. So this is also known as Lloyd's algorithm, with which for segmenting a particular image, suppose these are the pixels of the image and we want to segment it into two different clusters. Suppose the first figure is representing the pixels of the image and we wish to segment it into two different portions. Then you can easily take two different centers. One is this red particular triangle and another one is yellow triangle, and from these two things you can easily able to calculate the distance of all the points in and around it. Suppose if you will observe this red one, then all these points, they are very close to these red ones, and those which are very close to the yellow ones, okay, based upon the minimization of distance, you can segregate them into two groups. So if you will observe, we can able to calculate the distance, and thereby this particular line is partitioning them into two different groups. You observe that this red color becomes one-sided and this all yellow color becomes one-sided. Now the initial centroid we have taken, they were at extreme ends, okay, as they were randomly taken. So from extreme ends, we cannot able to control these particular groups. So that's why these centers, they will move on to the next mean values of these points. So whatever earlier this yellow one was there, that has moved to the central location, and this red color one is also moved to the central location. So that's why it is known as k-means clustering, because the center will move to the average value and thereby effective partitioning happens. So with respect to time, with the progress in iteration, if you will observe, with the progress in iteration, finally it has been segregated into two effective clusters. One is on this side and the other one is on this side. Okay. So over here it has been bifurcated into two different parts. So the k-means is especially based on minimization of Euclidean distance. So this is the expression for the Euclidean distance minimization. And same way Manhattan distance also can be taken. Its minimization can be formulated as a segmentation problem. So over here, this is the expression for the update of the center, and this is the condition to check that whether the optimality has been achieved or not. So over here, with k-means based segmentation of a hyperspectral image, an example is given over here that the fire at Eastern Arizona that happened in 2016 has been bifurcated into 4 clusters. So here you observe that this is leftmost part is the original image, and that has been bifurcated into one portion as smokes, another portion as fire, and another portion as greenery, and another portion as terrain region. Similarly, here the image of Astral Island that has been bifurcated into two different portions. One is containing all the portions of land, other one is all the portions of the water. But you can observe that the water portions are with different levels. So you can further segregate into different portions in which the depth of water levels are there. And they can be further clusters into multiple partitions. So we have observed that with k-means clustering algorithm, it has been formulated as an optimization thing, optimization of the distance between the cluster centers to all the data points of that particular partition. That means if we are considering an image from each point, each pixel values of the image to the cluster center, so we are determining the minimization of the distance so that we can effectively able to partition it. So based upon the partitions, like k-means clustering algorithm, there are many other algorithms are also there. Okay, but many of the times these algorithms get trapped in local optima solutions. Okay, that means they always follow a hill climbing based approach to get into the uh, solutions where they get trapped in the local optima. So in order to avoid that one, nature inspired algorithms have been reported over the years by several researchers. And most prominent algorithms in this category are evolutionary algorithms, like the genetic algorithm, which was invented in 1975 and then further applied to clustering in 1994. And all of you know that these algorithms, they do not follow the regular gradient descent based approach, and that's why they are more prominent to determine the global based solution. And such kind of algorithms are, if you are considering only one particular objective function, that is minimization of distance, to do the partition or segmentation, then that is known as a single objective algorithm. If you are trying to develop the cluster analysis with consideration of multiple objective function. Multiple objective function means one is minimization of distance, other one may be maximization of correlation. So under that circumstances, it will become a multi-objective algorithm. More than 2 or 3 functions you can able to use to perform this image segmentation. So for under the circumstances, the algorithms have also been reported by researchers, like non-dominated sorted genetic algorithm NSGA2, that is reported in 2007. So similarly, like the genetic algorithm, there are many other algorithms have been reported by researchers, like the swarm intelligence based algorithm. So swarm intelligence is collective intelligence of a group of birds, group of creatures, and most popular algorithms are particle swarm optimization and colony optimization, and they have been effectively applied for the image segmentation and cluster analysis. So like by swarm intelligence based algorithm, there are bio-inspired algorithms. There are many other nature-inspired algorithms that have been reported over the years, and they all have been applied effectively for the cluster analysis. So the most prominent algorithm, one is particle swarm optimization, that was in 1995 by Eberhardt and Kennedy, where they have proposed that a group of creatures, they do have the intelligence to determine the optima of a uh, optimal location. Like if you move to near a pond and throw some amount of food particle, then the fish which is very close to this particular food particle, that will observe the particular food and that will try to move there and then send a signal to its friends, and all of their friends have moved there, migrated there. So in such type of behavior is known as swarming, and with swarming you can able to solve many real life problems. So that same thing has been formulated over here as mathematical expression. You can observe that on the left side, this is the pond, with this particular one is the food source. And in the food source, there are a lot of fishes are there. Suppose this particular fish is very close to the food source and that has observed this particular food, and that is giving signals to all its rest friends. So this is the global driving particle, or we can say that this one is the global optimal solution that is driving the swarm towards the food location. And after the velocity and position update, you can observe that after certain time, all these particles, they all are moving close towards the food source. They all are moving towards the food source. So how they are moving, that is formulated as mathematically like this. This is the position of the particles, xi. This is the velocity associated with the particles. Pi is the local based position and Pg is a global based position of this one. So considering these particular locations, this is the velocity update of each particular particles, and corresponding to velocity update, the positions get updated. So the position at any k plus 1 iteration is its previous position plus the updated velocity. Okay, the updated velocity has been added with the position to determine the new position of the particles. And this velocity update, it depends upon the previous velocity. If you observe that VID k plus 1 is a weighted factor multiplied with the previous velocity. So this weight is known as inertia weight, which is multiplied with previous velocity. That means inertia weight means you can say that a particular bird or fish is swimming in a particular direction that has a tendency to move in the same direction. So it can move slightly left and slightly right, and it will try to go near to the food source. Okay, so that movement of inertia from that particular thing, it has come as inertia weight. W is the inertia weight. Okay, then there are C1, R1, and the particle present local based position minus the present position. C2 are two constants, and particles global based position minus the present position. So two things drive a particular particle. One is the local based position, and another one is the best position among the swarm, whichever is the best. That one. These two things try to drive this particular particle swarm towards the global solution. So when you move in that particular thing, the particles positions and the particles velocity, both of them has to be truncated. Okay, they have to be bounded within a maximum limit. Otherwise, what will happen? They will move out of the periphery, and you cannot able to catch hold of those particles. They will be of no use. They will be searching here and there in random locations, okay, outside the search space, which is of no use to us. So when their velocity becomes very high, you try to articulate some formulation with which you can truncate the velocity. And if their positions is much more, you can try to articulate such a position that they can be truncated. So this is a beautiful flow of the particle swarm optimization algorithm, and it can effectively be used for partitioning these particular clusters in which the image centers, the centers I defined you in the k-means clustering algorithm. Here the particles will be representing the centers of the clusters, and they try to move from one location to the other location so that you can effectively able to get the optimal partitioning. So like I told you, one of the example like the particle swarm optimization algorithm, there are many other nature inspired heuristics that has been reported by the researchers. And if you follow their workflow, then you can easily get the optimal solutions or optimal set of clusters for the analysis. Like I told you, Euclidean distance minimization. Similarly, many other kind of distance minimization also give you effective cluster analysis or effective segmentation. You can observe that many distance minimization have given the results. Some other functions maximization also can give the effective results for the cluster analysis, like Selhuti index maximization, Okay, Dunes index maximization also give us the effective results. And these are the researchers, they have already used these statistical uh, functions for effective cluster analysis. So if you want to look at more on these, their data clustering algorithms and their applications for the hyperspectral imaging, you can refer our review article. Okay, that this particular one is a comprehensive survey on these particular algorithms for the effective partitional clustering on a very popular journal of swarm and evolutionary competition, Elsevier. So let me introduce you another nature-inspired algorithm, which is compared to PSO, a recently reported one is known as social spider algorithm. Okay, this algorithm is more preferable than the PSO when we wish to get accurate solution. Okay, why it is preferred over the PSO? Because it is a multi-agent algorithm. What is the difference between a single agent and multi-agent algorithm? Try to understand. In particle swarm optimization, if you are initializing 10 particles or 10 pieces, they all are representing one type of entity. If there is a velocity update equation is there, that velocity update equation will be applicable for all the 10 particles, whatever you have initialized. But if it is a multi-agent algorithm and you have initialized 10 agents, 10 search agents, out of them, 5 of them will behave one type, 5 other will behave another type. So over here in this particular swarm intelligence algorithm, the entire number of spiders is bifurcated into 3-4 type of spiders, like the male spider, the female spider, and each of them will have different set of weight update. Okay, their velocity and position weight update equations will become different, and the search type will become different. So that's why they are multi-agent algorithms. And second thing is their update equations is different than that of the particle swarm optimization one. Particle swarm optimization always takes care of linear movement, linear directional vectors, whereas these algorithms are not also take care about nonlinear movement of the creatures to achieve the optimality. Okay, so to the optimal position you can move nonlinear manner and reach to the global optimal point. So considering this particular algorithm, here the algorithm movement is restricted on a wave, like here a wave-like structure is there on which there are multiple spiders are there, and the black color ones, they are the male spiders, and the uh, brown color one are the female spiders, and obviously there are some baby spiders are also there. So considering the nature of the algorithm as inspired and reported by the researchers that 60 to 90% of the population, they are represented as female spiders, and 10 to 30% they are male spiders. Based upon the programmer, you can decide it by your own. And from there we will have a percentage factor that will be that has to be initialized, which will be representing the female socialization behavior. And what is its role, that we will be discussing when we will be discussing about the way to update procedure for this. Okay, so over this algorithm, when we are considering, we have to first initialize the population. That is how many particles we are going to consider or search agents. Here normally suppose you are taking 100 spiders as the solution. Each spider represents the cluster centers. Okay, like I told you, in k-means the cluster centers are important. Over here also each particular spider is representing the location of the cluster centers of the various clusters. Suppose a particular image you want to segregate into 3 or 4 portions, then each particular portions will have one particular cluster, one cluster center. So if you are taking 4 partitions, then there will be 4 cluster centers will be there, and all the 4 cluster centers, they represent one particular solution, that is one particular spider. Like that, there will be 100 spiders you will be defining. That means 100 cross 4, that will be representing each one will have 4 cluster centers. So like that, the initialization will take place. So considering that one, now you have to evaluate that which particular spider is behaving good and which one is not up to mark. So that one you can able to do with a fitness calculation, that is known as fitness evaluation also. So with fitness evaluation, what we are trying to do is each particular spider we are calculating, they are representing the cluster centers. So from the cluster centers to the rest of the points, if they are behaving good or bad. So intra-cluster distance is one of the criteria with which we can able to make out compact clusters. So over here, the intra-cluster distance minimization for compact cluster is taken as the criteria for the fitness function. Okay. So after that, we can able to assign the weights to the spider. That is nothing but a function of the fitness of the spider. If it is a healthy spider, then assign more weight. If it is a not so healthy spider, then you assign less weight to that particular one. So considering the, I told you further partitioning of this particular spider, that whether the particular ith spider has more value than the average weight of the spider, then they will be treated as one type, dominant male spiders. Otherwise, they are treated as non-dominant male spiders. These particular bifurcation have been done because we want to make them into segregated into different groups, and each of the group will have their own type of weight update equation to do either exploration of the search space or exploitation of the search space. So when doing a global search, always exploration and exploitation, two processes are very, very important in case of any particular algorithm. So I told you that among communication among the spiders, over here there is the local spider and the global spider. The communication happens in such a manner that if the spider taps on the wave, then that tapping will generate a ripple, and that ripple will slowly die down. So if it is, if the spider has tapped over here, then it will create a very large pulse, and with respect to the distance, the pulse strength will be reduced. It is a exponentially decaying function with respect to the distance, if you will observe. So that's why over here, this weight of the spider into e to the power minus delta si minus sl square. This exponentially decaying function is very, very important. That exponentially decays over the thing. And this si minus sl, this is Euclidean distance. So delta SISL is local spider to the present spiders Euclidean distance. That one e to the power minus that square has been taken into account for designing this particular principle. Okay, so this is for the local one and this is for the global spider equation. And with that, the update equations you observe that those which are 60 to 70% female spiders we have considered, they are especially responsible for exploration of the search space. So with exploration, the update of the spider is taken over here. That depends upon two important factors. One is random number is lower than the probability factor. Okay, and there is otherwise condition. So there are two different weight update equations for the female spider to search the entire space. So this is the movement of the female spiders. Similarly, for the dominant male spiders, this is another update equation for towards the female and the dominant male spider. the weight updation is like this, and that is followed by exploitation of the search space, which is normally done by the non-dominant male spider, and this is their weight update equation. Okay, so all the three type of spiders do have three different type of characteristics, and that followed by the mating. So with the mating operation, you can able to observe that between male spider and female spiders, the mating operation happens when they are within a particular region, and this mating operation is mathematically defined like this, that suppose there is one male spider and three female spiders you can observe in a particular colony, and the position and weight. So which one will be the baby spider's location? So the baby spider's location will take place based upon the female spider or the mother's location, which will have the highest probability of occurrence. So if you will observe that among all these things, the highest probability of occurrence is F2, okay, because its probability of assessment is more. How we able to calculate the probability of assessment? Because the weights we are considering this 0.4, 0.3, 0.5, 0.29. If you make sum of them, if you make sum of them, that is equal to 1.49. So 0.4 divided by 1.49, that is 0.26. So probability is 26% for the M1. And similarly, so for F2, you can able to observe that the probability is 36%, which is highest. So the new baby spider will take that of this 36% and this 0.1 and 0.5. So it is taking the same location as 0.1 and 0.5 for the next generation. So in the original social spider algorithm, this females update, the dominant male way update, and the non-dominant male position update, all these three things have been put sequentially one after the other. Okay, whereas we have developed a parallel version of the social spider algorithm in which all these three things have been put in parallel. Okay, so when these things are put in parallel, obviously you can run them in multiple cores, and you can easily save the computational timing also. So we have tested it on various small dimensional data sets and various big dimensional data sets, as well as on the hyperspectral image analysis problems. In some of the things, we have got effective results, that is minimum classification error percentage compared to the other benchmark algorithms. This is one analysis on one very big dimensional data set. You can observe that here also the results are very effective, good clusters. And when developing the parallel versions, obviously I told you that the timing will be less. So compared to 44 seconds, this is 25 seconds. Compared to 35, this is 25 seconds. So computational time saving is one of the another important thing. So when we applied this algorithm for hyperspectral image analysis, you can observe that this is a hyperspectral image taken of the flood affected areas of Chennai. This is before flood. The amount of water retention we have able to calculate. You can observe that this is the seashore. So near to the seashore, you can observe that near to the seashore there are very less amount of water before the flood which has affected on December 9. And you can observe that in this particular one, when we did the image segmentation and try to determine the portion of the water which is there. So over here, you can observe that near to the seashore, a lot of water activities have happened, and these small lakes, they have grown up. You can observe that here there is a very small portion of the lake, but it has grown, and this river which is not visible over here, that is clearly visible over here in this particular portion. And a lot of water portion have grown in this particular area. So if you observe that by timely giving the information to the authority, the peoples living in these particular areas can be warned, so that they will not do the deep ocean water activities at that particular time, because that will be risky for their life. So uh, I have taken much time on the image segmentation point of view. So there is within a very small time, I will try to wrap up the second particular problem of the hyperspectral imaging. So the second problem is this particular raw image, especially the band selection. I want to say this is a university image and it has a lot of bands. So considering this particular thing, the image is very difficult to process. So you can do the band selection and select few bands for this particular image, okay, which will be very effective for the analysis. And then you can perform the clustering and do the effective analysis of the clustered image. So over here, for band selection, various type of mathematical tools you can able to use, and some of the mathematical equations which we have already used for the analysis are the first statistical function we have taken is variance of first spectral derivative. That is one particular function which you can able to minimize, so that there will be maximum similarity. What we want that if there are 100 bands over here, we do not wish to take those bands which are having similar kind of information. We want the bands which are exactly similar information, they should be dropped. And those which are possessing dissimilar information, those will be kept together. So fast spectral variance of fast spectral derivative is one aspect, and the other aspect is entropy measure. Okay, so entropy between different bands that you can able to consider. It minimizes the uncertainty among the selected bands. Then coefficient of variation is another particular objective which you can able to consider. The higher value of coefficient of variation means less similar information is present among the bands. So there are three objectives I told you. Considering three objectives, you can able to solve it as a multi-objective optimization problem, like the NSGA2 and NSGA3 algorithms that have been reported by Professor Kalyan of Michigan State University. And this is his website. And the NSGA3 algorithm, which is very, very popular nowadays, you can refer to this particular paper on the IEEE transaction in 2013. Okay, and this is the part one, and part two also contains a lot of application, and these algorithms codes also you can download from his Michigan State University website. So this original NSGA3 algorithm, we have also reported a binary NSGA3 algorithms, which is very effective for the hyperspectral image analysis, and we have reported it in IEEE Congress on Evolutionary Competition, and it has lower computational complexity compared to the original NSGA3 algorithm. So this is the flow of the algorithm, and I want to highlight with some results over here. You can observe that there are more than 100 bands are there in the ideal partition, and with binary NSGA3, few selected bands have been selected. Only the white color ones have been selected, and that many lower number of images we have considered for analysis and obtained significant partitions to this particular image. Okay, So this is the hyperspectral image of Pavia University, where the greenery portions have been designed like this, and this is the building and many other portions. So with the results of binary NSGA3, it has been effectively determined. So with another application also, we have observed the motion of the clouds in a particular zone. With binary NSGA3 algorithm, the cloud has been clustered and their movement have been captured with this particular algorithm. So like this, for various real life applications, you can able to develop algorithms for effectively analyzing these hyperspectral images. And you can refer our websites and the Google Scholar for obtaining a lot of details about the publications that we have done over the years in this particular research. Okay, so I hope I am in time little bit compressing the second problem, but that's fine. So that much from my side. If you have any queries, you can write your queries over here so that I can able to answer them now. So we have an option over here for the charting. So you can write your chart. Yeah. Uh, So one question have been raised by Bobita, one participant, that how effective is this social spider algorithm when integrated with deep learning frameworks for hyperparameter optimization. Obviously, we have I used other algorithms like the gray wolf optimizer and whale optimizer for the hyperparameter optimization for the deep learning network. You can refer one of the research paper on this. So this particular algorithm can also be applied for training the hyperparameters of deep learning networks, like how many number of layers you can able to take, how many number of neurons in each particular layer you can able to take, what should be the learning mu value you can able to take, optimal values. So these kind of hyperparameters you can effectively able to train with the with this type of algorithms. That is another aspect of solving a problem also. I hope I could able to answer your queries. Any other participant, you can write in the chat.
Sir, I think there is no more questions.
Okay, fine. If there is any other questions, you can also write over email to me.
Sir, there is one more question.
Okay. Yeah, there are several type of new algorithms have been reported over the years, and various type of mutation scheme, crossover schemes, weight update schemes that have been reported by various algorithms. So you should follow what is the corresponding mathematical logic behind the algorithm, and how this particular weight update equations they especially help. So that one will be very much helpful for you when you will follow the particular algorithm. Try to look at the mathematics behind that. Okay, so that is a very important aspect. So any other queries by the participant? Yeah, I think no other queries are there, no further queries. So I think our next speaker has also joined.
Yes, sir.
And
Okay, sir. I sincerely thank Professor Ajay Nanda, sir, for an enlightening and engaging session. Your valuable insights have truly enriched our understanding. Thank you, sir. We will go forward for the second session.
thank you, sir. And also I welcome our next speaker. Thank you. Namaste.
Namaste.
I am also the coordinator of this Electronics and ICT Academy, especially with which we are organizing this particular course and many more similar courses with the funding from Ministry of Electronics and IT, METI, Government of India. So I welcome you, sir. And
Thank you.
Your expertise will be definitely very much helpful for the participants, especially. So, Dr. Deepak, our academic person, please introduce, sir.
Yes,
Okay.
sir. Yes, sir. Dr. Deepak sir has done his PhD and masters from NIT Rourkela in the field of image processing and computer vision. He has worked in Microsoft and Mercedes-Benz. He has 8 years of industry experience in the field of self-driving cars, large language models, and vision language models. So with this introduction, sir, we are looking forward for your session. Thank you, sir. Over to you.
Thank you.
Okay, sir, you can share your screen.
Okay. Is my screen visible to you all?
Yes, sir, it is visible. So that you
Okay,
can do
so
full screen.
just a minute.